Okay, so here we are back at the end of this test where you want to show them again?
Yeah.
So there's the square wave and sine wave that we have sampled from both 10 kilohertz, one of them at 2 volts peak to peak, the other 3 volts peak to peak. And here we are about to import them into MATLAB and show that the average difference is less than 5%. So what we want to do is first we're going to import the data from our scope. And that's pretty simple. Import process. And here we're going to import the data from the text scope. 14 lines of header. It's sad that I know that. I'm going to call this something else so we don't overwrite our data. So now we have both of them imported, and if I open them up here you can see now I'm going to pull out the important data for each channel separately. So the way I'm going to do that is say our scope channel, and we could put a transcript of this all up on so you can run the exact commands over again if you're worried about it. Right now I'm just extracting the data that is for each channel rather than leaving them together in one variable. So now I have both the data for both of our scopes. And now I already know that since the text scope is sampling at 50 megasamples per second, or 50 million, as you can see there, and it's sampling a 10 kilohertz wave, we know that one period should be roughly 5,000 samples. And so we've gone ahead before doing this, gone through the tech scope data, and I can show you real quick if you want. On the first channel, to find out where one period exactly starts, where basically the zero crossing point is, and that point is at 463. So there's our zero crossing point, or at least our first one. So what we're going to do is say text scope channel 1 equal to data 2, and since they're sampling at 50 megasamples per second and we're sampling only at 1 megasample per second, we're going to take every 50 samples, which is what I'm doing with this command here, out of the 5,000 sample total data. So that should give us exactly 100 samples, and it does. That's this guy right here, exactly 100 samples for that waveform. We have basically now we're extracting equivalent samples from one of their waveforms as with one of our waveforms. And now we'll do the same thing with the second channel. Again, we found where basically the edge was on the square wave, and found that transition point. Now we're going to take every 50 samples of that for 5,000 samples to attain, again, 50 samples equaling an entire section, or entire period, I'm sorry. So now we need to basically do the same thing that we did with their data with our data, because we have a little over 5 periods here. So we've gone ahead again and done that ahead of time. You can see that the zero crossing point here is at 48. So I'm going to take our data and pull out exactly one channel, or one period of it. Sorry, I'm a little trying to type and talk at the same time. It's harder than it looks. So now we have one period on the first channel, and the second channel is basically done the exact same way. Again, we found the edge of the square wave, and found that it is at basically sample 5 to sample 104. And now we have basically both our samples and their samples equivalently. We scaled everything down, so we have 4 different data sets, all with 100 samples in them, and the samples should be equivalent on channel 1 and channel 2. So what we're going to do is take the difference between them. The difference for channel 1 is equal to our scope, the samples that our scope measured on channel 1, minus the samples that the text scope measured on channel 1. And we'll do the same thing for channel 2. Now we have the differences between the two. Now we need to take the average of that, average percent difference. So the way that we're going to get a percentage is we're going to divide by the total strength of the signal. This is something that we talked about a little bit. If we just divide by what that sample is supposed to be, then the smaller the sample level, the smaller the difference will result in a small difference will result in a large percent error. So for instance, if you had a sample that was supposed to be at 0.01 and you were at 0.02, well, that's only a difference of, a hundredth of a volt, or very small in comparison to the total signal power. You're actually off by 100%. So the way that we're doing this is we're taking the mean difference, and the absolute value so that doesn't affect it. Mean difference of channel 1 divided by the total signal power of channel 1, which is 2 volts peak to peak. And that here will give us right around 1% difference between our samples and the equivalent samples on the text field. Let's see here. As far as the other channel goes, we'll do the exact same thing. And that is a 3 volt peak to peak signal. And we see here that that's about 3.5% difference. And this one we expect to be a little higher because this is a square wave. So if we miss 1 or 2 samples on the edge of a square wave, that we get different than the text scope, which is a lot higher. Then rather than just being on a sine wave where it's exponentially increasing, we get it where we were supposed to have negative 1.5 volts and we measured 1.5 volts. So there's a big percent difference for maybe a couple of samples there, but for the rest of them, we're right on. And you can see that here with just the percent differences, 3% and 1%.
Cool. Also, if you're wondering where that error perhaps could have come from looking at the wave, we noticed a couple of things trying to search for where it came from. First, we're using 10x probes in this test, and we're measuring relatively small signals, 2-3 volts. So we're attenuating by a factor of about 40 or so on both channels, and then having programmable gain amplifiers amplify it back up, which means that for these tests, our programmable gain amplifiers are as high a gain as they are going to allow. So a lot of noise, if it's very small noise, can get coupled in and then amplified back up and look like a significant portion of our signal. And we think what's going on here is right at these edges where the square wave is transitioning, we get a slight blip in the sine wave as well. You can see those right there. So that probably accounts for a lot of what we're seeing in terms of error in this test. And I think that's about it.